Hi, I am Mohammad Jabari Far. I am a PhD student at the Mechanical Engineering Department working on the suspension of snow particles.
Hi, I am Shol Chakraborty, PhD student of Department of Electrical and Biomedical Engineering. Today, our topic is modeling the impact of destination strategies in a heterogeneous network using the SIRS model with a time-varying transmission rate. So, infectious diseases is a critical public health challenge, particularly if we consider the connected and heterogeneous populations. And also, it gets worse because of the time-varying transmission rate. It changes because of different reasons. To control the disease, we need different kind of extension strategies. In this study, we study on the time varying transmission rate and different kind of vaccination strategies.
We are using SIRS model in this study. We suppose that we have a heterogeneous mean field approximation, and we have a time varying transmission rate. Actually, for vaccinated individuals, we suppose that the transmission rate reduces to 1 minus rho times beta, which 1 minus rho is the reduction factor. We consider four different vaccination strategies. The first vaccination strategy is the initial randomly, which all the people gets vaccinated at the initial time, and these people are chosen randomly. The second strategy is the same as the first one, but the people that gets vaccinated are the people that have the highest degrees. And in the third strategy, we choose people to get vaccinated step by step. For example, if we are going to have 100 iterations, and we want to vaccinate 50 people in these iterations. We vaccinate at each iteration, we vaccinate 2 people. And these people are chosen randomly in the third strategy. And in the fourth strategy, it is the same as the third one, but instead of choosing people randomly, we choose people with the highest degrees. And we consider 2 different network configurations. The first one is the network configuration with the geometrical degree distribution. The second one is the network configuration with a Gaussian degree distribution. And we investigate the effect of vaccination percentage. We consider 40% of people gets vaccinated and 20% of people gets vaccinated, and we compare the results. And we investigate the effect of transmission rate, and we investigate the effect of parameters in the Gaussian degree distribution, and we compare the results for geometrical degree distribution and Gaussian degree distribution. Here you see the equations for this method. And here the results for the first part of this study are shown. Actually, based on these figures, we can conclude that the first strategy is the worst one. For none of row values, we can suppress the outbreak of the outbreak. But the first strategy is the best one, which for row value of 0.3, we have a suppress of outbreak, and we have the least peak values. Actually, here we can see the results for 20% of people, and 40% of people gets vaccinated. And we see that for the 40%, actually we can suppress the outbreak at a lower value of rho. And here are the results for the beta 0.3 and beta 0.5. And as can be seen, for the beta 0.3, we can suppress the outbreak at a lower value of rho. And we also investigated the effect of beta 1 and beta 1 and beta 1.1 and beta 1.3. And as can be seen, actually we see higher amplitudes for beta 1 of 0.3.
In this slide, we actually check the different parameters of the Gaussian degree distributions heterogeneous network. For this case, we varies the mean average, that means average degree, and when the variance is fixed 5, we use the fourth Bayes extension strategy, and Bayes extension percentage is 40%. We see that when mu is average degree is increasing, we need high rho factor to reduce the arc break. In this case, we simulate our Gaussian degree distribution heterogeneous network with different kind of variance. In this case, average degree is 5, and Bayes extension strategy and Bayes extension percentage is same as the previous simulation. We found a similar result pattern, and for this case, when the variance is increasing, we need higher rho factor to reduce the outbreak. This is the histogram of degree distribution for both geometrical and Gaussian network that we use to compare both of them. And this slide is showing the the comparison between the geometrical and Gaussian degree distribution. We see that for both cases, we use the same Bayes extension strategy. That means fourth one, step by step degree-based Bayes extension distribution, and Bayes extension percentage is 40%. For both cases, we need higher rho factor to reduce the outbreak. For the geometrical one, the rho factor is more than 0.4, and for the Gaussian one, rho factor is more than 0.5. Okay, this is the this conclude our study. We use two kind of degree distribution. One is geometrical and Gaussian distribution. Distribution for our SIRS model with heterogeneous network. We use time variant transmission rate. We also use different kind of Bayes extension strategy, and we found that step-by-step degree-based Bayes extension is the best one. We also do some investigation on the Bayes extension coverage and transmission rate, and also different kind of parameters study on the Gaussian degree network. We hope that this study will have a huge effect on the public health policy and everything. Thank you everyone for listening and watching. Have a good day.